Let's see. Okay, so as far as the daily homework goes, you can either print out that Fourier graph, or you can just, if you have it on your laptop, you can just as well show it to me, and as long as it looks reasonable, that's fine. I'm happy either way. We have our exam this Thursday. I won't be here till probably 10:30 or so, and so I won't have you start it until I get here. But it's the same format as anything else. Just so you know, there's some people in engineering who are interested in kind of normal modes, which we're gonna be getting to soon. So I invited them to these talks. So if you start seeing like random people here, well, who aren't the right part of the day, they're basically grad students who are interested in normal modes, who may or may not be here. Don't pitch. Okay, so let's kind of set up what we're gonna do. And so we talked about why we need to reformulate. Oh, good morning, Richard.
This morning.
So it just said that some grad students might be doing it, and this is good. She's working with Professor Collins on vibrational densities of states and various systems.
I think that we also want to come, but I don't know.
Okay.
No.
If they can come, they can come. You're always welcome.
Thank you.
Why we need to reformulate classical. Let's Newton a second. Okay, so we said if we have a problem like let's take this. Let's say here's mass, pulley, something like this. Let's say it's going down like this. Okay, so we got all the forces on our block there. Yep.
Tension.
Tension. Normal.
Right.
Obvious, right? And then maybe there's friction, maybe there isn't friction. It's just like that. Called kinetic friction. And then we set up a coordinate system, which would be what? Yeah, always take the way the system moves to be the coordinate system. So since it's moving this way here, you're gonna get something like this. Okay, that's how I set this up. All fine, good. Now we said the problem is if we have something like this. Let's say we get that. And then we have a block here like this. Let's say it's coming along here. We're gonna say what's the coordinates? What are the forces on it? Well, here it had the normal, here it had the weight, and I would neglect friction just because I had neglect friction. But if I'm over here, this is the normal, and here's the weight. If I'm over here, then this is the normal, and here's the weight. From here, this is the normal, here's the weight. The normal keeps on changing here. So the normal force is constantly changing. So we can't set up an easy coordinate system like here. Here I could have one fixed coordinate system. Here I can't. So it is not possible to have one coordinate system. Analytically. Now I could do this with I could set up a computer program. I could I could just have a coordinate system like this. Set up kind of, if I knew the shape of this curve here, I could set this up and I could do it numerically that way. But it'd be remarkably hard to do it analytically. That makes sense. And so what we're going to do, I'm going to call this normal force here a force of constraint. And so since the mass must move on the surface, it's the normal force. Okay, so we call this a constraint. Okay, so we're going to say that this mass here is constrained to move on the surface. And any forces connected with that motion, we're going to call a force constraint. So any forces associated with this constraint are called forces of constraint. So what we want to do is I want to reformulate the F equals ma to get rid of those forces of constraint, and primarily the normal force. So we'd like to reformulate F net equals ma so that normal forces, I'll say, i.e. forces of constraint, are not present. And when we're done, F equals ma is not going to look like F equals ma. It's going to be remarkably abstract. Okay, so just again, this is a preview. Okay, so this is, we will see that F equals ma is going to become d by dt, partial of L with respect to Q I dot. And don't worry too much about what that is yet, because of partial of L with respect to QI. And this L here is going to be the total energy of the system, total kinetic energy of the system, minus the potential energy of the system. And this is going to be nothing but F equals ma in a very, very, very remarkably abstract. Okay. And when a physicist does actually really advanced physics, they are almost always using that. Okay, so if you pick up an upper level physics book, quantum mechanics, any type of thing like this, guaranteed this is either going to be that this is going to be assumed you know what this is, or it's going to start you, one of the two. Okay, now we're just doing it. Oh, in the end, you're going to know and love this equation. It's going to be one of the most important equations you ever have in physics. Okay. If you do particle physics, this is what you get. The standard model, what it is, it's really a big Lagrangian for basically how particle physics works. That's what it is. It's basically it's called the Lagrangian, and it's going to be a big Lagrangian for the system. So the standard model is a Lagrangian for basically all particle physics, and it's this big unyielding thing. Okay. So we said in order to do this, we need the idea of degrees of freedom. So in order to do this, we need to understand degrees of freedom and generalized coordinates. Now we started this on Friday, and we kind of got it toward the end of the class. Let's go back through it again, and we'll sort of have this. So we talked about the number of degrees of freedom. Okay, what did we say the number of degrees of freedom are? It's the same idea that we had actually had. Oh, we're gonna build up at that point. We're gonna build up at that point. But it's the same idea that we had in the physics of class course. It's going to be the number of independent coordinates we need to specify a system. So if I basically have a system, there's a certain number of coordinates I need to basically put all those pieces in my system. That's what they are. Okay. So this right here, this is going to be the number of degrees of freedom. I'll just start abbreviating it like this. Is the number of independent. Okay, and the independent part is the really important. It's the number of independent coordinates we need to specify a system. The actual coordinates that we use for these are then called the generalized coordinates, and we call them the Q's. Okay. The independent coordinates that are used are called the generalized coordinates. Okay, Q. If you have more than one, then you call them Q sub I. Okay. So let's take an example here. Let's say I have a mass here. Like this. And let's say somehow I can have a pendulum. Yeah. Don't worry about how this string somehow gets to the floor. Let's not worry about that part. But we're going to assume that this mass can swing like this, and the mass can go back and forth like this. Okay. So the question is, how many degrees of freedom do we have for this? Okay, so this can go back and forth, and that pendulum can go back and forth like this. So how many coordinates would I need for this? And this is going to be motion in the plane. This is the motion. Right? The masses are confined to motion in the xy plane. Okay. Now we're hearing 2. Now degrees. So the number of degrees of freedom is 2. Now, what would they be? First of all, there's more than one answer to this. Because what I'm using for 2 and what you're using for 2 might be different. And that's perfectly fine. Yeah.
See, the first one is the horizontal of the mass in the spring.
Yeah, that's what I would do. So what we have here is, let's call this, I have like a dotted line here. I call this the x equals 0 position of the spring. So this is basically the equilibrium position of the spring. So I'm going to say from here to there, I'll call this x. So that's 1. So I'll call this one Q1. So that's my first generalized coordinate. Okay. What else?
Horizontal, the component of the
Yeah, I could just as well say that than this distance from here to there. I could call this x2, so I'll just call it x. I'll just call it x2, and then this one here that I can call Q2. Perfectly fine. But somebody else might say, I like this one, but I don't know. Perfectly fine. What else could you do? That's actually what we're gonna do.
You could have like an angle.
Yeah, somebody else would say, I don't really like that. Somebody else would say, because this is fine here, this is my Q1. Then I'm gonna say that this right here, this is my angle here, this is theta, and that's gonna be this would be my Q2. Perfectly fine. Now, it turns out this one's gonna be more convenient. Okay, so in this case here, the Q's, you have a Q1 which is X, and a Q2 equals theta. Over here, what would you do? You'd have a Q1, which is X, and then a Q2, which is this X2. Okay, which one is correct? They both are. They're both gonna work. Now, it turns out, because I've experienced with this and you don't have, okay, that this is gonna be a lot easier to do. Okay. Now, there's a so let's figure out what's going on here. So there's actually what's called some constraints. Let's beat up this a little bit more. So in this problem, what are the constraints? So what are the constraints in this problem here?
Length, right?
The length of the string is 1. So one of them, the length of the string is fixed. Okay. Here's another one.
Angle.
Well, the angle can be anything
Mhm.
because it can go back and forth.
The floor.
More that we're saying that this mass is constrained to move on the floor, right? It's not. It has to appear as the floor, right? It has to back and forth like this. It's not going to go up like that. It has to be that. No, we didn't state that. It's going to apply to the problem. That would be a force constraint. So another one would be M is constrained to move on the horizontal surface. Okay. Now let's actually go through and let's assume we have 2D motion, only 2D motion. Okay. So normally, right, in 2D, each particle would have. Okay, so if you have one particle all by its lonesome in 2D, how many degrees of freedom does it have? 2, an X and a Y. So each particle would have 2 degrees of freedom. Basically, you would have an X and a Y. So in this problem here, how many, again, turn off all the constraints. We turn off all the constraints, how many degrees of freedom would we have here? We'd have 4. We'd have X and Y for this one, and an X, Y in this one. So in this problem, if we ignore the constraints, there would be 4 degrees of freedom. I'll say in X and Y for each of these. That makes sense. So now what are we getting? We're actually saying that the number of degrees of freedom, okay, is going to be 2 times n minus the number of constraints. So this right here is the number of constraints. And this n here is going to be the number of particles. So in this case, what would we have? This is the number of degrees of freedom. It'd be what? It'd be 2 times 2 minus, we have 2 constraints that are 2 And this is 2. So that's why we have two degrees of freedom. Does that make sense? Why would we still have 2 if I did 3D motion? It's still the same idea here. That this has to move this way here, and that this is going to be in the XY plane. So no. If we considered the same problem in 3D, but keeping everything else the same. Motion the same. We would still have 2 degrees of freedom. Now, how come? Yep.
Spring only stimulates motion in one direction, and so
So that's introducing how many constraints?
2 for
Correct, right? Because we're saying that the Y motion is 0. Okay, but what are we saying about the Z motion as well? Okay. I shift to the Z motion. So this is Y and this is Z, right? We're only allowing motion this way. So there's 2 constraints here. Okay, that's 2. This is still fixed. 3. Well, what did it say about the motion of this guy here?
Can't move.
It can't move, it has to stay in the XY plane, so the Z is 0. That's our 4th constraint. So in a case like that, what we would have is that now we would have the number of degrees of freedom. Okay, is 3n. And why do we have a 3n now? Because each particle could have x, y, z. Okay, minus the number of constraints. So in this case, we've got 3 times 2 minus 4. All right, so what this would be is that this 4 here, we would have z1 equals 0, z2 equals 0. The mass here itself, I'll say y1 equals 0 here. L is fixed. Is fixed. So 1, 2, 3, 4. Does that make sense? Questions? Okay, so everyone good with that? So if I had an ideal gas, how many degrees of freedom would an ideal gas have? How many particles would there be?
Long.
Okay, n. So we'd have, right, we'd have n particles. What does it mean to be an ideal gas again? I think statistical mechanics is all for next semester. So we're going to ideal gases in extreme detail. Well, you probably had enough chemistry. It's something to know what an ideal gas is. What does it mean? What do you ignore? Particle interactions. So you basically are treating all these particles as independent. So how many constraints do you have? None. Because you have n particles, no constraints. So if I had an ideal gas, how many degrees of freedom would I have?
2 again.
I'd have 3 n. Okay. That makes sense? Questions? Okay, so what are we going to do with this? Okay. So since the QIs are independent variables. Okay. We can write the positions of all of our particles in the system as functions of the QIs. Okay, I gave you the name for the QI. I've been up since my brain is completely flushed. I gave you the name for these as being generalized coordinates, right? Okay, so the QIs are generalized coordinates. We're going to generalize velocities and generalize momentum in just a moment. So what I can do is I can actually write the position of the first part as a function of all my Q's. Q-pen. I can write the position of my second, whatever that is, as a function of all the Q's. Okay, in principle, there could be a time as well here. Too. There might be an explicit time dependence here. These Q's would all be implicit functions of times. And I can do this for all my particles. Okay, better not use n. Why should I not use n?
You might have.
N is usually going to be the number of particles in the system. I'll call this n. Okay. So m equals the number of degrees of freedom. N is going to equal the number of particles in a system. That makes sense. So let's just do a little example here. So what would I have in a case like this? I'd have basically my coordinate for this guy here. This would be just x, and that would be a generalized coordinate. But now what I have for this guy here, I can have this coordinate here. Here's x2. And I then call this right here y2. How can I write x2? This distance is, right, this is L. That distance is
L sin theta.
L sine theta. You add this to it, x, so this would be x plus L sine of theta. Right. This right here, this x2 here. This x2 is a function of my q1 and my q2, right? Because I'm saying that this is q. That makes sense. Then what would I say about y2? I'd say y2 would be what? I put a minus sign in there because it's going downward. Minus L cosine theta. This is again, this is saying my y2 is a function of my q1, which in this case has no functional dependence on it. Q2 is off. Okay. That's what that means. That makes sense. Okay, so is everyone good with that? Okay, now here's where I told you before on Friday, I'm gonna give you the real derivations for this expression here. This is the book I'm gonna use. This is the book I had in graduate school. This is an old friend of mine. We've gone through a lot together. I like this book a lot. It's one of the classic books in classical mechanics, the standard graduate text. It's by Goldstein, Herbert Goldstein, classical mechanics. It's probably, okay, I think it's an absolutely amazing book with the exception of the relativity chapter, which is not that great. Other than that, I think it's an absolutely brilliant book. A lot of people absolutely despise this book. I don't. This is again, this is an old friend. This is hello, old friend. Okay. I'm gonna use the derivation that we have in here, because it's, it has all the details, but it's gonna be a little on the abstract side. In order to reformulate. In order to reformulate Newton's second law, which we will use D'Alembert's principle of virtual work. And I want to set this up. So we define a virtual displacement of the ith particle as delta Ri such that we define a virtual displacement of the ith particle. I shouldn't define it, I should say we call it, but I won't change myself. This is bad English. Delta Ri such that it occurs at a fixed time and is any motion consistent, any displacement consistent with a constraint. Okay, so I'm going to give you, I told you before, I had a professor in grad school who, as far as I can tell, is the only one who has ever really explained in detail what this means. Usually, if you ask somebody what a virtual displacement is, they'll say, well, any displacement consistent with a constraint. Okay, so what's the virtual displacement? I'm not sure. So this is an example. Okay, so let's say I have a pivot here and I have a rod here like this. So this rod can move back and forth like this. I'm going to have a mass here like this. This is the mass. And the constraint is that this mass must move along the rod. I'll call this head. So the constraint on M is that M must move along. That's constraint. Okay, so I want to show you what an actual displacement is, and then what a virtual displacement is. Okay. So what would be an actual displacement here? An actual displacement would be what? If I redraw this picture, I'm going to make it a little more shallow. This is at time t. What's going to happen is that an actual displacement, is going to mean that this rod is going to move here. And this rod is going to go here. And so this right here, that would be my dr. This is an actual displacement. So this is at some time, this is at time t plus dt. If the rod moves down, what's gonna happen is that has to move over with it. That makes sense? A virtual displacement is not that. It occurs at a fixed time. So when you have a virtual displacement. Oh, and also I want to do one more thing here. Okay, how's the normal force go here? The normal force right here looks at what? It's like that. A virtual displacement is this. A virtual displacement of them occurs at a fixed time. So here's a rod. Like this, and here's this. And this is t equals a fixed time. Okay, so what would be a virtual displacement? I take a snapshot of my picture, and then I can move any piece I want independently of the other, just as long as it's consistent. So what would be a consistent motion for this right here? It has to stay on the rod. So if I move this particle over to here, that right there, that is a virtual displacement. The constraint is the particle has to move, has to stay on the rod. And a virtual displacement has to be consistent with the constraint. Okay, so this right here, this is the virtual displacement. Okay. It is not the actual displacement. Okay. How's the normal force look here?
Same.
It's the same. There's no change here. Hey, what do you notice about this normal force and this virtual displacement here? Compared to the normal force here and this actual displacement. Over there, it is perpendicular. Here, it is not. So note. N is perpendicular to delta R. But N is not perpendicular to dr. And you look at that and say, well, isn't that one? Actually, it is. Or am I still clear? I am still clear. And again, my professor is from the wild. He's the only one, as far as I can tell, that has ever made that. I've never seen anyone else in any book where they actually have gone through and actually explained that. He was a very intimidating professor. He's scared the hell out of me. Well, I wasn't the only one. Excellent teacher, just not a cuddly professor. But he was a good professor, just not cuddly. Questions to that. Okay, so now let's actually connect this together with the principle of virtual work. Okay, so let's start with seconds. So let's talk about the virtual work. So how do we define virtual work? Well, virtual work, I'll call this delta W. Will be by definition, it's going to be the force on something. Let's say this is for the airport here. Dotted into basically the virtual displacement. How do we normally define work? Well, normal work. Is defined as and I'm talking about for an infinitesimal displacement. It's going to be this Fi dot dri. So we just have the exact same normal definition here, but we're ready. Okay. Now what can we do with this? Okay, so let's start off with, so right. F net equals MA for the X particle. Okay, so first of all, we have to do a little bit thing. Usually. We don't write MA as MA. Okay, that sounds like a stupid statement, okay. MA in more advanced physics. Is written as, and we've actually seen this in general physics. So it's one of those things you see it, you don't really think a lot about it. How else how do you think we're gonna write it? And so we have MA. What is a formal definition of A?
X.
Well, we'll do this R double dot. Okay, so I could say that this is R vector double dot. How else can I write R double dot? Oh, do you know what a dot is? Jim, do you know what a dot is? It's a time derivative.
Oh.
Okay, so dot equals this. So you could just as well write this as this. Yeah. Well, how else can you write a second derivative? Meaning, how can I write the acceleration? That's perfectly correct. It's a time derivative of the velocity, right? You can just as well say that this is really m times the time derivative of the velocity. Yeah, I can take that mass inside here and write this as d by dt of mv. Does mv have a name?
Yes.
I agree. It is our friend.
Momentum.
What kind of momentum? Linear momentum. Okay. So this would be just regular linear momentum, which is the same thing as saying p dot. So normally when you have F equals ma, the way it's almost always going to be written is this. I can write this as an F net on the ith particle. That's going to equal, I can say this here, or just simply pi dot. And if I wanted to find the net virtual work on this, what would I do? I would just do this. That makes sense. Now, what I'm going to do is I'm going to take this to the other side. And I'm going to pull out my virtual displacement. And how many particles do I have? N of them. So what I'm going to do is I'm going to sum this over all the particles in my system. So I'm going to write this as a sum from I equals 1 to n of F net I minus pi dot my delta Ri equals 0. Okay. It's still clear. I still am clear. Okay. Now, I can take that total force. I can really say it's going to be broken up into two parts. I can say that all the forces acting on my system are either applied forces or forces of constraints. So what we can do is I can actually say that this right here is really going to be all the applied forces acting on the output particle, plus all the forces of constraints acting on the output particle. Okay, minus this guy here. Equals 0. Now this is too hard to keep on writing it like this. So this one here, I'm just going to call this F applied. Okay, and then this one here, I'm just going to define this to be now put a little bit here. F sub C. So a more compact way of writing this is this way. Okay. Now, here's the magic that's going to occur. Okay. We know since forces of constraint are perpendicular to delta Ri. Right? We saw that with the normal force. We can conclude the sum on I from 1 to n FCIC dot delta Ri equals 0. Those forces of constraint are always going to be perpendicular to any virtual displacement. So what does that leave me? Exactly what I want. That will leave the sum on from 1 F here minus this guy here. Delta Ri here equals 0, and this is called D'Alembert's principle. Of virtual force. Okay. And what we'll do tomorrow, and it might have to go into Wednesday as well, we're going to write this all in terms of the Q's. Okay, so tomorrow. We will write D'Alembert's principle. In terms of the Q's and virtual displacements. Of the Q's. In other words, see it's delta Q's like that. Okay? And it's going to be a little more involved than you think. Okay, and what this will lead us to are those equations that I gave you. And then we'll do a whole bunch of examples of this. And then, and again, you're going to see that we're going to be able to tackle problems that if you try to do it with F equals MA, good luck with that. Okay, we're going to be able to tackle a whole series of problems that right now with your background you can't do. As soon as you have this, the whole world opens up to you. Who's in advanced lab? You? Oh, you. Okay. You're probably going to be doing normal modes on the, have you done the normal mode lab? Yeah. The strings, I think you probably will. This is how you're going to analyze that extra. We're not there yet. So you're going to use this approach in, okay, I don't know if the other ones have had classical mechanics yet. So that you might be getting a lot of people saying, hey, Jake, how's this work? So you might be getting a lot of questions. Okay. Okay, this is going to be abstract for a while. Okay. It's not gonna become any less abstract tomorrow. This is already is an, again, I'm giving you the graduate derivation. Partly because any other derivation doesn't go through the details. And it just comes across as, I don't want to keep them like that. It's really, there's a reason for it. Okay, well, what have we done today? We've removed the forces of constraint, and that was the whole point of today. Okay, so tomorrow we're gonna rewrite this and it's not quite Shazam, but it's almost Shazam. That will have been Lagrange's equations. Okay, every day.
Tomorrow will be.
Tomorrow we're gonna we have classes on Monday, Tuesday, Wednesday, Friday.
Okay.
And you're welcome to come to any of them. And again, it's gonna be the same. This will be at the same.
Thank you.
Yeah.
At that time.
It's all they're all at 9:20.
9:20.
Yeah, you're all at
Thank you.
9:20. Same bat time, same bat channel. Okay.